All right, so today we wrap up Chapter 3. We're going to cover not only a quick review of one fin's performance, but what happens when you have multiple fins on a surface, and you can talk about an overall surface efficiency and overall performance of the finned surface. This we did last time, the derivation of the analytic solution for the temperature profile. The key part of this table 3.4, is for the adiabatic condition. And so what we have is we have an analytic expression, the simplest of every one of these in this table, except for maybe for infinite length. But you have that the theta divided by theta b, or the temperature as a function of distance x as you move from the base 0 out to the tip L, minus T infinity, the fluid temperature, is equal to divided by temperature at the base minus T infinity. That's what theta is, isn't it? Theta is temperature minus T infinity. Okay. What was this parameter m? Well, it's a parameter m, HP divided by K A sub C. Does it have L in the equation? Does L affect lowercase m, the parameter m? Does L affect? Does H affect it? Does K affect it? Thermal conductivity, yes. Does the cross-sectional area affect it? Does the perimeter affect it? Does L affect it? No. Good. And then also, if you wanted to find the rate of heat transfer out that single fin, Q sub F is equal to cap M. Oh, another parameter. There it is. It's H, P, K, A sub C, square root of all that times theta B. Does L affect cap M? No, it doesn't. It doesn't affect it. But it affects the flow of heat, or the rate of heat transfer through that fin, through the hyperbolic tangent of M times L. M times L. All right. We don't spend a lot of time on non-uniform cross-sectional areas, but they have a lot of fins that do have it. It's just that the math is cumbersome, and maybe you would go to numerical solutions and correlations based on numerical analysis of some feature. But here's parabolic, here's triangular. I've never given an exam question that required you to do anything but uniform cross-sectional pin or rectangular fins. But the book has more. And even you could have radial fins. They're out there in practice. They're very important. I just choose not to have test you over those. I figured if you can handle the other fin arrangements, then if you needed to in practice, you could figure out how to use charts and others for annular fins. All right. Let's solve this problem. So we have a brass rod. When you see the brass, you say, well, let's go get the thermal conductivity of the brass. It's about 110 watts per meter degree C. Its length is 100 millimeters. L is equal to 100 millimeters. I just ended a number of conversations with students. It's like, Professor, my only error is this. Well, get rid of that error and don't make that error again, because it's painful to you to take a lot of points and throw them down the tubes. So I'm going to ask a clicker question. I would like L in units of meters. So the answer can be A or B or C or D or E. Is it 0.1 meter, 0.01 meter, 0.001 meter, 0.0001 meter? What is 100 millimeters in meters? I'm not asking a hard question, am I? Everybody in? Is everybody in? I'm going to shut it down, okay? So we'll go ahead and stop. And the probability that we're 100% correct? Well, I know I make mistakes too, but learn to double and triple check yourself. Let's move on. It's similar to a lot of other things in there. All right, so we get that, and I like to do it this way. Why do I like to do it that way? So it helps me avoid my own mistakes in life, and I make a lot of them. All right, so now we have the diameter, and it's 5 millimeter. I suspect I want that to be, you see the logic in me writing it like that? I find it less error prone. All right. Sometimes I may want to work in radius. I would write that down too, but I think I can handle diameter. But if you want to handle, you say, I don't want to ever do anything in diameters, I want to do radius. Well, write a line with the radius and be done with it. It extends where you have the base temperature of 200 degrees C, and it extends into the fluid where the fluid temperature is 20 degrees C, and a convection coefficient of 30 watts. I didn't write 30 very clearly. 30 watts per meter squared Kelvin. Look it. Can I just do that? Yep. Please, if you like to convert everything to Kelvin, but then you make a error doing it, you will not be pleased with the number of points taken off. All right. What is the temperature of the rod at 25 millimeters, 50, and 100 millimeters from the base? So I'm asked to find, and I'll introduce some symbols. I'll say T25. What is that? The temperature at 0.025 meters, isn't it? And I'll say I'm asked to find T50, and I'll ask to find T100, right? So let's just go ahead. How do we solve for that temperature? Well, we just covered the analytic temperature profile, T minus the T infinity divided by the temperature of the base minus T infinity equal to the cosh of M times L minus X, L minus X, divided by the cosh of ML. Professor, we're going to have to memorize that. That's on your equation sheet, true? That's on your equation sheet. So all I have to do is substitute and solve. Let me just say that I have to calculate M. So that's going to be the positive square root of the HP divided by KA sub C. Let's think it's a rod, right? So what is the perimeter? Pi d. What is that cross-sectional area? Pi d squared over 4. And when you put in the value of H and the K, you'll get that M is equal to 14.771 over M. Did I mention that this is very confusing? Because I have M in the equation, once on the right, once on the left. But the M's mean different things, don't they? What is the M on the left? A parameter. What is the M on the right? Units of meter. So when you look at this equation, it's like, what? This is nonsense. But that M, well, I wish they would have maybe not used M, but maybe beta. I don't know. You know, just so to avoid the confusion. Then it would have been beta is equal to 14.7. But this book didn't use beta, so let's get rid of it. And I can't remember other books. I think a couple other books I know use M. So we're stuck with it, okay? Hopefully you didn't find that too confusing. So when we stick it all together, we could find that the temperature at the distance 25 is 150 degrees C. The temperature at 50 is 120 degrees C. And the temperature at 100 millimeters out is 97 degrees C. This is one time when one box will suffice. Yes?
What tells me this is an adiabatic process?
The adiabatic tip? Oh, yeah, you helped me make the correction there because I forgot one thing. We want to use the corrected length right here and the corrected length right there. And then that accounts for then we can use a simpler adiabatic tip. So in this equation, when I calculate the 150, 120, and 97, I used the corrected length, which is the physical length, plus the diameter over 4. So when I add the diameter over 4, it's 0.1013 meter compared to right here, 0.100 meter. Sorry, you saved me. Thank you. Ready to press forward? In the homework, there's a problem that says find L such that 0.65 is equal to the hyperbolic tangent of 37.1 times L, all of that, divided by 37.1 times L. So guess what the parameter M is in this equation? 37.1. That's what the parameter M is with units inverse meter. And 0.65, that's that fin efficiency, 65%. How do you solve that problem? I'm going to do this. I'm going to pause. I'm going to walk around the room, and I want you to work as hard as you can for the next 3 to 4 minutes to solve this problem. And if you can solve it, you raise your hand, and I'll come over, and I want to see how you solve it. All right, so one way to do this, and I strongly encourage you to do it, not only using your calculator, that's the preferred route, but the slow and tedious route, going back to your numerical methods textbook and reviewing something like the secant method or the bisection method. Everybody passed numerical methods, true? You didn't throw away the book? So go look at bisection or secant method. It's after the Newton-Raphson technique for root finding. And one good way to do it is to put in a table x and then the function of x that you want to be equal to 0. So this function of x in this problem, x is L. That's how we interpret it. And what's the function? 0.65 minus the hyperbolic tangent. I can't write this, sorry. Tangent of 37.1 times L divided by 37.1 times L. Does that make sense? So now I'm going to show you how to do that without the root solving on your calculator, but you would need to, it helps if you program it up in your calculator, but I think the easiest demonstration right now is in Excel. So what I did was I said, I'm thinking of finding x such that f of x equals 0. That's what I want. Well, I'm going to put in a sequence of L's because L is what I'm interpreting to be the x. Somebody said the L needs to be about 0.04. Maybe I'll use that as the first guess. So I'll come over here, and what is my function? It's 0.65 minus the hyperbolic tangent of 37.1 times L. I know I'm putting that not as an equation, but I'm trying to type it out so you can see it, divided by 37.1 times L. True? So if I just expand this cell, that's what we're trying to implement. I'll go ahead and copy this because I don't want to retype too much. And I'll say, let's now evaluate it. But L was not L. It needed to get this cell for L. And this L, get rid of that and put that cell for L. Won't that work? And so that's pretty close to 0, isn't it? Maybe I started, I didn't know what it was. Maybe I guessed that it was 1. Well, if I guessed that it was 1, it would be 0.623. Then I'd say, well, maybe it's 2. Well, if I evaluate it at 2, it's 0.636. It's going further away. So maybe I go not to, maybe 0.5. Oh, it's getting smaller. Okay, 0.1. Getting even smaller. See what I'm doing? And then you go 0.05, getting smaller, 0.02. It crossed the sign. See, it's now negative. It went across. So I know it's between 0.02 and what was my last one? 0.05 or 4. So it's in between those. So if you're doing it by hand, you would report all these and show it converging. You give it to your calculator once you know what you're doing, and it can go a little faster. But this is just one of those 0.025, I don't know, or 0.03. 0.03. It's still negative. Got to go above that. That's by hand, trial and error. I recommend you do it at least once in your life. Make a little table and play with it. But then learn how to use the tools that are accessible to you during your exam and the rest of your career, your calculator. True? All right, let's move on. Oh, what was the final answer? I think we already put that in there. 6.1, something like that. That's pretty close to 0, isn't it? Drives it to 0 pretty good. Very good. Don't save. An array of fins. Now, we're going to be able to come out with, considering not just one fin on a surface, but an array of fins. And so when you have an array of fins, typically they don't change much. You have a pile of them and they're attached to the same surface. So what you do is you bust it into a symmetry section and then you analyze it. The smallest symmetry section would be a cut here and a cut right here. Those would be symmetry lines. You could see that if I just cut there and cut there, then I started flipping top to bottom, top to bottom, I could reproduce the whole system, right? Well, that one's convenient, but it's almost more convenient if I grab a symmetry that goes this far. So I can grab a larger symmetry section which isn't the smallest out there. And so what I have is I have the heat transfer that's going from here, which is all at the temperature TB, out into the fluid with H and T infinity, characterizing the fluid. It'll be the sum of what goes through the fin and then into the fluid or through the base. It's not covered by the fin. And so the total Q going out will be Q that goes to the fin plus Q that's uncovered base. All right. And so that's the QB and the QF. And what you want to do is just like we had a efficiency for a fin. Remember that equation? We'll also get an equation for the efficiency for the O. I know why they put efficiency. That symbol's the same. What is that Greek letter eta? But the subscript F for a single fin, why did they put the O? What is the meaning of the subscript O? It's the overall efficiency for a finned surface, accounting for both fins and bare surfaces. That's why the O, overall efficiency. What is my equation, before I try to derive it, what is my equation for the overall finned surface efficiency? It's 1 minus the number of fins times the area of each fin divided by, this is the area of one fin, and then divided by the area total times 1 minus eta F. Okay, let's make sure we understand each term in here. N is the number of fins. A of F is the area of one fin. AT, what do you think the T is for? Total area that the fluid's in contact. Okay, all right, let's slow this down a little bit. We also had the efficiency of a fin, right? Okay. What we're going to do is we're going to think about neglecting the tips. We'll use that approximation that the tips are well insulated and we have a corrected length, L. All right, that's fine. So what would be the area for one fin? If I just have the symmetry section, I have L going out and going back, it's W going back, right? Okay, so for one fin, remind me, what is A sub F? Area one fin is 2L plus the 2 T's, but we can often neglect the 2 T's, they're small. If you wanted to put them in there, then it's the 2 thicknesses. This is the thickness T. True? All right. the total area, A sub t, this is the total area, is going to be the area of one fin plus the area base, right? Well, we have to have the magnitude of the area base. The area base is going to be some distance. Let's just call this the gap right here, cap H. I don't think they actually introduce it because you just need to be able to calculate it. Or, okay, they introduce this. They have cap S, which goes from there to there. Hence, the area for the unexposed base AB is equal to cap S minus T. So it's back to this dimension only, times W. All right. That will be for each fin. That will be for each fin. So the total area for each fin will be just, I don't even want to reproduce it, 2L plus 2T plus S minus T times W. I forgot. 2L plus 2T times W, right? Got to multiply by the W. Running out of room here. So you look and you understand the terms for the areas and the number of fins, and we already understand the single fin efficiency. Well, this gives you an overall fin efficiency. Let me ask a clicker question. In general, the efficiency of the fin, how would it compare to the overall efficiency? Would it be greater, equal, less, or it all depends? It could be all above. All above. So answer A, answer B, answer C, or answer D. D is basically saying some problems it may be greater, some problems it may be less. We can't really say there's a general rule. The overall efficiency compared to the single fin efficiency. Is everybody in, or you need more time? I'm going to talk about the problem some more and then ask the same exact question. Okay, now here's a question for you. I know that they never introduced the efficiency of the unfinned base. What? The efficiency of the unfinned base. But if you had to introduce, if the textbook doesn't introduce the efficiency of the unfinned base, but if you recall what the definition of the efficiency of the fin surface was, that was the Q maximum, actual, divided by the Q maximum, where the maximum is if all of the fin surface everywhere is at the temperature of the base. Right? Right? So let's say I follow that analogy. The efficiency of the unfinned base then would be either greater than 1, equal to 1, or less than 100%. All of those are 100%, right? 100%. I'll answer that A, B, or C. And struggle with that one. See if you can come up with the answer for that. Are we doing this on herd instinct? You know, after tonight, there'll be a lot less presidential candidates. Are we locked in? There was a little herding going on. Did you see it? A little shifting. I've got to stop this. And let's take a look at this. The efficiency was this actual rate of heat transfer. If it's off the base, what is the actual rate of heat transfer? The convection coefficient, area of the base, times theta at the base. All right, what would be the maximum? That would be the maximum if the temperature of the base was the temperature of the base. It would be H area of the base, theta base. The eta of the base that makes sense is 100%, nothing above. True? So it's like we have an efficiency of transferring off the base of 100%. We have efficiency, let's say the fin efficiency is 80% off of that part of the surface. And maybe the area of the fin was divided by the area total was, 80%. 80% of the area that the fluid is in contact with the surface is off of the fin. And that would leave 20% of the area being the base area divided by A total, because the sum of the two fractions would be 100%, right? And this efficiency is 100%, and this efficiency maybe 60%. What do you think about the efficiency of the overall surface? Would it be less than 60, equal to 60, or greater than 60? So I ask another clicker question here. Sorry about this. Is if for this example I say that I have an area total. Let's say the area of the fin is 0.8 meters squared. The area of the uncovered base is 0.2 meters squared. The area total, hence, is 1 meter squared. Hence, 80% of the area that the fluid's in contact with the solid is due to the fin. 20% is due to the unexposed exposed base. And we just talked about the base is 100% efficiency. And we're just making up the fin to be 60% efficiency. Then I ask you, what would you expect the efficiency of the overall system to be? And so the overall efficiency would be less than 60%, equal to 60%, between 60 and 80%, not 60 and 80%, or greater than 60%. Answer, too many options, A, B, or C. Let's go ahead and see what you can come up with. You ready? I'm going to stop it. Yeah, which one are we voting on? I feel like I am missing the boat here because I'm not asking questions that you're engaging with. The problem with this section is we can get lost in the math. And I think that some of the equations could be maybe presented a little clearer to the student as he tries to learn the material. But I'm trying to make sure you have some insight. And unfortunately, I'm not helping you build that insight, am I, as a class? Man, I don't know how to say it, but if you're getting sort of 60% efficiency and 100% efficiency, but you're going to blend them together where 20% weight of 100 plus 80% weight of 60, doesn't that come in a little greater than 60% overall? Yeah, isn't C the right answer? I don't know if I could make an analogy. Let's say I have $1,000, and I go and I put it at $200 in a bank at 8% interest, and I put in $800 at 4% interest. What's going to be my total effective interest on the whole $1,000 that I put into both banks? You know what I mean? They're combined. Will it be, less than 4%, between 4 and 8%, greater than 8%? What will it be? It'll be between the 4 and 8%. And so this is what we're doing is just that this is 100% and that's 60%. But all right, I have failed you. I don't know how I'm doing this so poorly. We already graded that one. Are you ready to go back and grade this one? It's hard to see in the mathematics, but the efficiency here is going to be maybe 60%. The efficiency associated with the unbinned exposed base is going to be 100%. Hence, the overall efficiency is going to be greater than the single fin efficiency for the finned surface. So the overall efficiency is going to be greater. Isn't C? And it's really hard to see from the equation. Hopefully you can physically reason through it. All right, I'm done with that. Okay, I have to press forward, but we are able to analyze some systems which apparently appeared pretty complex, like a system of fins. Here is a hot base and a hot base. Maybe you have some electronics dissipating, and so you want to convectively cool them. So what you do is you have passages where the air flows through it, and these passages are made of some high conductivity material. And so can you see what these little passageways look like? They look like half fins, because I don't make the problem too complex. Make this temperature the same as that temperature up there, so it's symmetrical, and then I can cut it through the middle and then just look at one edge. So I come down, I have a fin, I come down, I have a fin, I come down, I have a fin. And truly, in this case, mathematically, they are insulated because it's a cut at the symmetry. Make sense? And then now I have this finned surface, and all along here is TB. The same thing, I have the convection off of this rectangular fin that goes back, rectangular fin that goes back. Like that. And the fluid flows only through there, that passageway. Okay. And so I want to analyze this system to see how much heat is dissipated. All right. We have the equations and they're developed, but what I would do is the same problem, but I would do this. I would first ask, before you are struggling with a more difficult problem, if you assume the fin efficiency is 100%, could you calculate the rate of heat transfer to the air for a single passage? And then, once you have it for a single passage, you tell me there's 250 passages. I think I know how to scale it up for the whole system. So think about this. I have one single passage. This is my symmetry. It's insulated out here, okay? And I'm interested in the Q. If I have the fin is 100% efficient, what does it mean about the temperature along the surface of the fin, anywhere along there, if its efficiency is 100%? It's the same temperature. I can dispense with so much mathematics and just get to the heart of the problem. I'll do this. I'll say, you know what? The Q for a single passage is going to be my convection coefficient times the area of the fin surface plus the area of the base for that one passage times the theta of the base. Is that equation good for one fin? Is that? And then you just say, okay, well, what's the area of this fin? And we'll go ahead and say this was L. Going back in that third dimension, W, trying to stay with that. True? And then I know that I tried to introduce a parameter like this, H, but I think the textbook uses what? This would be the parameter S for the textbook. And this would be the thickness T over 2 and the thickness T over 2, right? Because it's half thickness of our rectangular fin. So anyway, let's do it. What is the area of one single fin? L times W times 2. 2 is times 2. How many agree? That's just this one fin. I'm just looking at one symmetry section. Okay. Now the area of the exposed base. S minus T times W. True? And then you could calculate that. This is so easy. And let's say this. I then change the problem, and there is no assume that the fin is all 100% efficiency. You've got to go and calculate the fin efficiency. True? So for the second modified problem, I just come back here. What would I change? What would I change? I would have to say, well, the Q for the system with one fin would be the Q from one of the fins plus the base. And then the one fin would be the convection coefficient, the area of the fin, and theta B times the efficiency of that one fin, wouldn't it? And then I add to it the convection coefficient, area of the unfinned base times theta B. So really, this part right here didn't change, did it? The only thing different is the efficiency in the fin surface. Did the amount of area associated with one fin change? Nope. Convection coefficient, same. Theta B is the same. Now I just need to calculate the efficiency of one fin. Sorry, I don't have time to slug through this one anymore, but hopefully you would be able to do that. And then if I had 250 passages, I would just multiply by the number of passages and I'd have the total. Thank you very much for your attention.